Hello everyone. In this video, we're going to talk about derivatives and antiderivatives of exponential functions. To start with, I'm going to need to introduce a special number called e. You've likely heard of this number before, but let's make sure everyone knows what e actually is. To motivate the definition, let's consider a few typical exponential functions such as the ones you see here. And notice this y-intercept is common to all of these functions. In fact, every single exponential function passes through this point, but each of them does so with a different slope. And just to be clear, when I say slope, I'm referring to the slope of the tangent line at that point. And to make our study of exponential functions as simple as possible, we wish to consider a scenario where the slope of this tangent line is exactly 1. Because after all, a slope of 1 is as easy as it gets. And that's where we get the definition of a special number which we call e. E is defined as the number with the property that y equals e to the x has a slope of exactly 1 at the y-intercept. That's a bit of a frustrating definition though, because it doesn't really tell us what the value of e is, but you can figure that out at least approximately by using a graphing calculator. Because after all, notice if this line really does have a slope of 1, then the formula for this line must be y equals x plus 1, because the y-intercept is 1 and the slope is 1. So according to mx plus b, this would be the formula for that line. And using your own graphing calculator, you can check that this line is at least approximately tangent to the function 2.72 to the x. So that suggests that e has an approximate value of 2.72. It turns out e is actually an irrational number like pi, so I can't really list all the decimal values since they go on forever, but knowing that e is about 2.72 is as good as knowing pi is about 3.14, so this will serve our purposes just fine. Now, it turns out that this function, y equals e to the x, is important enough in calculus that it has a special name. We call it the natural exponential function. And similarly, the corresponding inverse function, which is the base e logarithm, is called the natural logarithm. But the natural logarithm comes up so often, it's annoying to literally write log base e every time. So we've shortened this a bit and we normally call it ln of x instead of log base e of x. ln of x is also frequently pronounced ln of x. So if you ever hear me say that, I'm just referring to this base e logarithm. One reason why the natural exponential function is so important is because it has a really nice derivative. Actually, it turns out that e to the x is the derivative of itself. You've probably seen this before in an earlier calculus course, but my guess is that not everyone watching knows why this is true. So let's prove it. The way you prove almost any derivative formula is by using the definition of the derivative. And that is this limit as h approaches 0 that I'm sure you wished you would never see again. But it is important that we still know this, so if you've forgotten it, I suggest pausing here and reviewing the definition of the derivative. But if you're comfortable with this, let's move forward. And notice the first term here contains addition in the exponent. So using exponent laws, we can express that as e to the x times e to the h. After doing that, we notice both terms in the numerator have a common factor of e to the x. So we're going to pull that out front, which just leaves us with e to the h minus 1 in the numerator. I'm actually going to pull that e to the x all the way out front of the entire limit, which I can do because e to the x won't be affected by h approaching 0. Now, for the moment, I want you to just take a bit of a leap of faith and believe me that this remaining limit has a value of 1, because if it does, then this whole thing can be simplified to e to the x times 1, and that would just be e to the x, which would prove that the derivative formula at the top of the screen is accurate. Now, this proof hinges upon my claim that this limit is equal to 1, so all that remains is to understand why that part is true. This is actually a consequence of the way we defined the number e. Let's recall that definition. E was defined with the property that e to the x has a slope of 1 at the y-intercept, or in other words, at x equals 0. And it turns out that this slope, the fact that this slope is 1 is exactly the reason why our limit is equal to 1. Let me clarify why that is. From your first calculus course, you should know that slope at x equals 0 means the same thing as derivative at x equals 0. And derivative at x equals 0 is what we call f prime of 0. So therefore, our definition of E tells us that f prime of 0 must be equal to 1. Now, f prime of 0 literally means that x equals 0 was plugged into the derivative, but when we do that, e to the x plus h becomes e to the 0 plus h, and e to the x becomes e to the 0. So this entire expression is just another name for f prime of 0, which we know is equal to 1. Notice that e to the 0 plus h simplifies to e to the h, and e to the 0 simplifies to a value of 1. So we end up with this result, which verifies my claim that this limit is actually equal to 1, which completes the proof of our derivative formula. Once we know this derivative, we can use it to come up with a few more important formulas. For starters, let's say we wanted the derivative of e to the power of u. Notice I've stated this as a derivative with respect to x, so by calling the exponent u, there's an implication that this exponent is something more than just an x. So the chain rule has to be applied here. But that's no problem. If the derivative of e to the x is e to the x, then the derivative of e to the u would be e to the u times the derivative of u according to the chain rule. We'll see some examples of this in just a moment. And finally, anytime we develop a derivative formula, we get an antiderivative formula for free. The integral I've written here asks, what is a function whose derivative is e to the u? Well, that would just be e to the u. Just don't forget to include the plus c for indefinite integrals such as this one. I suggest including all of these on your formula sheet since we'll be using them quite a lot in this course. Something I want to caution you of at this point is to be aware of the difference between a power function and an exponential function. We know an exponential function is of the form y equals a to the x, or in other words, a constant raised to a variable. But a power function is the opposite of that, a variable which is raised to a constant. We know the derivative of a power function is found using the power rule, so I'm guessing some viewers might be wondering, why is this not the rule we use for differentiating e to the x? And the reason for that is because e to the x is not a power function, it's a constant raised to a variable. Power functions are not the same thing as exponential functions, so we shouldn't expect their derivatives to behave the same way either. Let's take this derivative, for example. We know that we can take the derivative of each term separately, so let's start with this first term. Notice this is a constant raised to a variable, so we want to differentiate this as an exponential expression. We know the derivative of e to the x is just e to the x, so the derivative of e to the 3x should be e to the 3x times the derivative of 3x according to the chain rule. Notice that's necessary anytime the exponent of e is not just an x. Now we can take the derivative of this second term. Notice that this is of the form variable raised to a constant, so it's a power function. And that means the familiar power rule can differentiate this term as ex to the e minus 1. Now what about this last term? Is this an exponential function or a power function? Well, actually it's neither, because this is a constant raised to a constant, which on the whole is just a constant. We know that the derivative of any constant is just 0, and so with that, our final step would be to calculate this one remaining derivative, which has a value of 3. So after simplifying, we can present this as our final answer. Now let's see if we can calculate this derivative. Pause and try it for yourself, and when you're ready, let's look at the answer. First, notice we're taking the derivative of e to the power of something. We know the derivative of e to the x is just e to the x, so the derivative of e to the something will be e to the something, multiplied by the derivative of that something according to the chain rule. Now we need to take the derivative of this square root, which is done using the power rule. But since this square root contains something which is also more complicated than just an x, the chain rule applies again here, telling us to multiply again by that derivative of the inside part. This last derivative is just 2x, so we're done differentiating at this stage and we can present this as our answer. Generally speaking, simplifying beyond this point is not necessary unless there's a clear reason why you should. Now let's try taking an antiderivative. Earlier in the video, we learned how to take the integral of e to the u, but the question given to us appears to be of the form 1 over e to the u. So how can you correct that problem? Pause and see if you can solve this for yourself. I'm about to spoil it, so make sure you're ready to continue. I think the most natural thing to do is to use a negative exponent to make this more clearly match the form of e to the u. If we think of this exponent as u, we can see this formula we came up with might be applicable now. But be careful. Our integral in its current form reads e to the u dx, not e to the u du. If we want to think of this as e to the u, we need to do it properly by performing a u substitution. So calculate du by taking the derivative as usual, and use that to express dx in terms of du. Completing the substitution now gives us this result, to which we can now apply our formula. The integral of e to the u is just e to the u. Don't forget to include the plus c. As a final step, don't forget also to express u back in terms of x, and we're finished. Here's another example. Pause and try for yourself, and when you're ready to see the answer, let's continue. The correct solution to this problem is again motivated by the fact that we only know how to find the integral of e to the u. So it would at least be worth trying this as a substitution. So next, you'll find du using the power rule. You can pause and check these steps if necessary. And what you'll notice is that du contains this factor of dx over x squared. And that's something that also appears in our integral. So that strongly suggests that this substitution probably is going to work out well. So next, I'd manipulate this expression to see what dx over x squared is equal to, and that would be minus 1 over 3 du. And putting this together, this problem becomes the integral of e to the u, and dx over x squared becomes minus 1/3 du, making for a pretty nice result. We know the integral of e to the u is just e to the u. Just don't forget to include your plus c and express your final answer in terms of x. That's it for the calculus of natural exponential function. So I'll see you in the next video where we'll discuss exponential functions of a more general type.